mentioned before, with 5.5, 5.6, we're going to continue this fun journey and take a look at different probabilities of different situations. Back in 5.3, we were doing probability, just basic, looking at a probability distribution table, looking at, what's the probability of certain outcomes happening, and some of our basic rules of probability. Yesterday, we were starting to take a look at how do you set up a two-way table? How do you take into account probabilities that actually, or two events where we have to worry about the intersection, okay? And we started talking about probability of A and not B, or B and not A. Okay. Today, we're going to focus on two more things. One we've already talked a little bit about, but the biggest key that we're going to focus on here today is conditional probability. Okay? Basically, when we're talking about a conditional probability, we're talking about a probability, or calculating out a probability when given some known information. Okay? So what happens is we'll ask you to say, hey, calculate out this probability if you know this particular fact has happened. So when we talk about, again, conditional, you're going to find the probability that one event happens given that another event is already known to happen. So you know that something else has actually occurred. And with that information, does that actually change your probability? So when talking about a deck of cards, okay? So for instance, if I say, what's the probability that the card you draw is a jack, given that it's a red card? Okay, so you know it's a red card. So instead of looking at 52 cards, you're only looking at 26 cards. What's the probability that it's a jack? 2 out of 26, because there's 2 red jacks. Because you would know it's not a black jack, so it still would be, no pun intended there, it was saying blackjack, so. But it would be 1 out of 13. It did actually change the probability in that particular case. But I might say, what's the probability that I draw a jack on the second draw, given I drew a jack on the first draw? So that would actually change the probability, because there would be 1 less card in the deck and 1 less jack. So the probabilities can actually change. So we'll be talking specifically about those types of situations. Now, before we jump into an example, we want to give you some of the symbol notation. Okay? So as it reads here, it says the probability that event B happens, given that A has already happened, is denoted by this symbol notation. P of, so you want, the way I like to say this is the first event is what you want. So you want B, this slash represents the word given, A has occurred. Knowing the fact that A has actually happened. So, how we can calculate that out using a formula. And I'm going to show you how to use the formula and also how to, look at a two-way table and actually sometimes calculate it out a little bit faster and easier. This formula is very helpful where you have to actually lay out a diagram where you're looking at, as Amat was saying, drawing a second card or a third card or a fourth card. Okay? But if you're given a two-way table, it's sometimes easier not to use this particular formula. But if you look at how the formula is calculated out, probability of B given that A has occurred. On the top, you're taking a look at all the outcomes. So remember that this symbol is the same thing as and. So sometimes I rewrite it as this: the probability of A and B occurring, given that just the probability of A has occurred. Since you know that A has happened, you're really just looking at it at just the outcomes of A. You can toss out all the outcomes of just B occurring first. Okay. So, to show you how you can set up this problem and calculate it out. Okay. So, here in this first example, it says, let's look again at the who owns a home data given below. So we're using this exact same table from yesterday and doing Venn diagrams and calculating out some probabilities. So in question A here it says, if we know a person owns a home, what's the probability that the person is a high school graduate? So when I look at these problems and I think of the conditional probability, there's two events that I have to put in here. The first event is what I'm actually wanting to find the probability of. So when it says, what's the probability that the person is a high school graduate? That's what I start with. Is a high school grad, we used that abbreviation I think yesterday, HSG, did we? Okay, I just want to be consistent with yesterday. So I think my 4th hour class might have used a slightly different abbreviation. So is a high school grad given, what do we know that has occurred? Okay, that they what? Yeah, they own a home. So they own a home. So if I'm using the formula to calculate this out, okay, what I'm doing here is I'm looking at, well, what's the probability that they're a high school grad and own a home over the probability that they just own a home. So if I'm calculating this out, probability of having someone who's a high school grad and they own a home, how many students are homeowners and high school grads? 221 out of my 500. So I'm actually calculating out that probability. Divided by, what's the probability that I randomly pick a person who owns a home? 340 out of, whoops, I got ahead of myself, out of 500. I started writing 500 and I hadn't completed 340 yet. Now, if I simplify this fraction, I got a fraction over a fraction, so how do I clear out this fraction in the denominator? What do I multiply by? Okay, so just the reciprocal, opposite reciprocal or perpendicular lines. Okay. So we just flip, so multiply the top and bottom by 500 over 340. When you do that, what happens to the bottom? Cancels out or becomes 1. Anything divided by 1 is now just the top. Anything else simplify here? Any factors cancel out? I thought I heard someone say it. The 500s. So you're left with 221 out of 340. Now, I'm guessing there's a few of you in here that probably said, wow, that's pretty complicated to do this particular formula. Okay, it takes a few steps. Okay. The nice thing is the formula will always work. However, there is a kind of short, quick, faster method sometimes that is a little bit quicker when you have two-way tables. Okay. And this really tends to work when you're given the two-way tables. And if you're not given it, then doing this formula is much easier or faster. And that is this, okay? You know a person owns a home, don't you? Okay, so since you know that, you're just concentrating on these 340 people. Of those 340 people, how many are high school grads? 221. 221 out of 340, do you get the same answer? Okay. So, if you're given a two-way table and asked to do some conditional probabilities, they'll at least be able to write this in its formula. And if you can tell me the answer directly from a two-way table, I am okay with that. But there are times, as you'll see later, either today or tomorrow, where the formula is going to be very helpful. So, I'm going to show you both ways on the second one here, and have you help me out a little bit. B says, if we know that a person is a high school graduate, what's the probability that the person owns a home? So what comes first in my statement? Okay, it's probability that they own a home, given, okay, so is a high school grad. So now, some of you might be able to tell me what this answer is right off the top of your head. Just curious. Anyone know what this answer is going to be? 221 out of 310 is correct. Because you're concentrating on, you know they're just high school graduates. So you're only focusing on those 310 people. Of those 310 people, how many of them owned a home? 221. So if you can get to that answer right away, excellent. I am going to show you the formula. So the first part is, what's the probability that they own a home and high school grad divided by the probability that they're a high school grad. Well, here's the nice thing about this particular problem. Have we already calculated off the top? High school grad and own a home, is that the same as own a home and a high school grad? It's just flipping them. So the top number is the same, 221 out of 500. But when we calculate out the bottom, high school grad, we had 310 high school grads out of 500 total students. So now here, when I simplify, multiplying by 500 over 310, bottoms cross out, 500s cross out, and notice how you get the same answer. So you can see how your probabilities change based on a certain situation, or what I like to think, a certain condition has been given to you. Now, one of the nice things that we've talked a little bit already about, okay, is this concept of independent events. When the probability of one outcome doesn't change the probability of another outcome. The nice thing about conditional probabilities is you can also use it to show whether or not something, okay, is independent or not. Okay? So, the way you do it is this. Okay? If you're given two events and they're independent, it means the probability won't change, or the given information should not change your probability. So if I flip a coin and I get a heads on the last coin toss, does that impact me getting heads on the next coin toss? No, doesn't impact it. That's why flipping a coin twice, those are independent events. Okay? One way though we can show it algebraically is to say, well, in their conditional distribution, the probability of some event A, knowing that B has occurred, should not impact finding that probability of A. Known information should change the probability. So in a conditional probability, if you're calculating one out, if it ends up just equaling the probability of A itself, then you know the two events are independent. You can flip your letters around, and all it does is change that the probability of B given A has occurred. If that equals the probability of B, then it's A-OK. So to demonstrate this, the question up here asks, from the data of the problem above, is being a high school graduate and owning a home independent events? Justify your answer using the formulas above. So, I could think about it like this. Is the probability of owning a home, given that they're a high school grad, is that equal to the probability of them just owning a home? If those two probabilities are equal, they're independent. If they're not equal, not independent. Well, here's the nice thing. Do I have this probability here? Yeah. Isn't it the last one I just calculated out? It's the same as this one here. So 221 divided by 310. Does that equal, I'm going to put a little question mark, the probability that someone owns a home? Well, if I go back to my table, what's the probability that someone owns a home? You got it, 340 out of 500. Are these two probabilities equal to each other? Well, sometimes it might not be easy to see. 221 divided by 310. Let's turn that into a decimal. That's equal to 0.7129. 340 divided by 500, if you trust my math, 0.68 is correct. Are those equal? They're not equal. Therefore, owning a home and being a high school graduate are not independent events. Yeah. Okay, yeah, give me a minute here. Hope you feel better. Yeah. All right, let's continue on the next page. Now, modeling chance behavior that involves a sequence of outcomes. Right? This is what we call our general multiplication rule. So when we start to take a look at a sequence of events, like drawing two cards or drawing two names out of a hat, rolling a die and then flipping a coin and then drawing something out of a hat, something like that, where we're doing multiple types of probability outcomes. Okay? One of the things you can do is you can use this particular formula to help you calculate out the probability of A and B occurring. Okay? And how you calculate it out is simply by saying what's the probability of A times the probability of B, given that A has actually occurred. So what you're going to basically do is you're going to take the probability of your first event times the probability of your second event B, but knowing that A, the first event, has occurred. Okay. Now, the easier way to demonstrate these calculations, okay, is by what we do many times in probabilities is we like to draw out what we call a tree diagram. It shows and lists out all the different possible outcomes that can occur in a sample space. So to demonstrate a quick example here for you, let's take a look at this example here below. It says, in January of 2010, the Kaiser Family Foundation released a study about the influence of media in the lives of young people aged 8 to 18. In the study, 17% of youth were classified as light media users. Don't know how they classified light media users, but they have some sort of classification. Maybe it's like using media less than an hour a day. 62% were classified as moderate media users, maybe between maybe 1 and 2 hours. 21% were classified as heavy media users, maybe more than 2 hours a day. I don't know for sure. Okay. So, of the light users responded, 74% described their grades as good, so getting A's or B's, while only 68% of the moderate users and 52% of the heavy users described their grades as good. Okay. So in part A it says draw a tree diagram showing all outcomes and their respective probabilities. Okay. So what happens is here, when we want to draw a tree diagram, we have a point where we just basically start. And what we want to do from that starting point is draw branches from that starting point to represent all of the possibilities of the first event. What was the first thing they described in the situation? Okay? How often you used media, right? So we start with media use. Okay. So they gave 3 classifications of media use. It was light, moderate, and I believe, was it heavy? So now, what we like to do with a tree diagram is to write the probabilities along the branches. So basically, as I start here and I go to light, I write what's the probability that I would go along that branch. Well, according to up here, it said 17% were light media users. So as a decimal, I write 0.17. I continue to fill out the rest of the branches. Moderate media users, 0.62. And heavy media users, 0.21. So that's our first event. It's basically like saying these are my probabilities of A. Probability of being a light media user, a moderate media user, a heavy media user. So then I have my second event. Okay? And the second event talked about grades. So from the light media user, notice how they say of the light users responded. Okay. So they're actually saying based on the light users, so they're giving you that conditional piece. Here's the probability of B given that A has occurred. What's the probability of good grades given that they're a light media user? They're giving you that piece of information. Of the light users responded, 74% describe their grades as good. So we're going to say good grades, I suppose, for lack of a better term, bad grades. So 0.74. So what would be the probability for the bad grades? 0.26. We're going to do the same thing here for moderate. So according to the information, only 68% of the moderate users describe their grades as good. So 0.68 is good grades. While 0.32 describe it as bad grades. Then we branch off the heavy media users, good grades, bad grades. So here it said 52% of the heavy users describe their grades as good. That means 48 is bad. A couple things that hopefully you remember back in your Algebra 2 days when dealing with tree diagrams. When you take a look at one event and you look at all the branches off that particular event, especially just the first event, okay, these probabilities should all add up to 100% or 1. In this case, they do. Likewise, off of each branch or set of branches off a point, these add up to 100. These add up to 100. These add up to 100. Now, one of the things that's going to be helpful here is we're going to take a minute or two and do some calculations. So what I can do is say, well, what's the probability that a light user has good grades? Okay. If I randomly picked a person, what's the likelihood that they are a light user with good grades? Well, what I can then do is follow the branches and multiply these two probabilities together. I'm basically doing this calculation. The probability of a light user and good grades would be the probability of a light user times the probability of good grades given they're a light user. Well, that's probability of a light user. This is the probability of good grades given they are a light user. So I need to take a minute or two. I'm going to just slide this over a little bit so I can see my calculator and try to do these all at the same time and write them. So the first one here, I'm going 0.17 times 0.74. Well, I'm going to do these in red so we can see them a little bit better. So 0.17 times 0.74. We get 0.1258. Then 0.17 times 0.26. 0.0442. One of the things that I actually do when I'm doing my calculations so that I know I'm entering them incorrectly, guess what these two probabilities should add up to? They should add up to 0.17. Because I've taken the 0.17 and broken it up into two pieces. So I always do a little quick check and just kind of in my head say, do these two add up to 0.17? And in this case they do. So I do the same thing for the next set. So 0.62 times 0.68. So 0.4216. And then for the next one, 0.62 times 0.32, 0.1984. I can just do a quick check again. Do these two add up to 0.62? And they do. Do the last two, 0.21 times 0.52, 0.1092. And then the last one, watch this, 0.008. So I know these two numbers have to add up to 0.21, but just to show you, 0.21 times 0.48, 0.1008. Sometimes I can actually use how the flow of the tree diagram works and how the probabilities have to add up to certain values. Now, what should be true about all of these values? They should add up to what? They should all add up to 1. Do they? Well, if these two add up to 0.17 and these two, add up to 0.62 and these two added up to 0.21, did these at the beginning add up to 1? Yeah. So I know I've done all my calculations correctly. Very important to do. We hate it when we make arithmetic errors. I know I do. So, let's then use our tree diagram here, and I'm going to shrink this just a little bit so that I can still see the questions and my probabilities. So it says, according to the study, what % of young people say they get good grades? So, it does say percent, so I'm going to calculate out probability first and then change it to a percent. So I'm looking at what's the probability that a person gets good grades. So, which probabilities up there should I be taking a look at? I'll switch to like blue here. Okay, so this first one here, good grades. How about the second one? Third one? Fourth one? Fifth one? Yeah, so I need to take those three probabilities, and guess what I'm going to do with them? I'm going to add them together. So, 0.1258 plus 0.4216 plus 0.1092. Oops. Let's go to this one here. So 0.1258 plus 0.4216 plus 0.1092. So 0.6566. But they did say percent, so 65.66% of young people say they get good grades. Let's see, what's a color we haven't used? We haven't actually used hot pink here. Now we get into a little bit of conditional probabilities. It says, what percent of youth with good grades are heavy users of media? So what's the probability that you're actually trying to find? Or percent? Let me rephrase it this way then. What is the given information in this problem? What information do you actually know? What percent of youth with good grades? So I'm narrowing it on the ones that have good grades. So I know that it's a person with good grades. I want to know what's the probability then, knowing that they have good grades, that they're heavy media users. So the heavy media users comes first, given that they have good grades. So now, when I go to calculate this out, this is where the formula is very helpful. Because in the top, I'm looking at, well, what's the probability that there are, if you're okay, heavy media users. So I'm going to just underline that so you know where I'm coming from that. Heavy media users and good grades over the probability that they get good grades. So if I use my tree diagram, I can find this top probability rather easily. Heavy media users and good grades is 0.1092. What's the probability that they have good grades? Yeah, didn't we just find that? So we're actually going to use our answer in part B to help us calculate this out. So 0.1092 divided by 0.6566 is 0.1663. This equals 0.1663. Can you read that? Actually, it does show up okay. So we could say the percent of youth with good grades that are heavy media users is 16.63%. All right, let's take a look at our last one here. It says, what percent of youth with not good grades are light media users? So now we're saying probability of light media users. So what's the probability that they're a light media user given that they have not good grades or bad grades? So in the top, I'm really looking at the probability of them being light media users and bad grades over the probability of them having bad grades. So to get the top number, I can use my tree diagram. Light media users and bad grades is 0.0442. Okay. Probability of them getting bad grades. How in the world am I going to get that one?
You have to add up all the grades.
Okay. So you could add these up. What's another way I could probably get it pretty quick? Probability of bad grades, this should equal 1 minus the probability of good grades. So you could add them up, or I'm going to do it this way, go 1 minus 0.6566. That equals 0.3434. So, one last calculation in one sentence. 0.0442 divided by 0.3434, 0.127 So we could say the percent of youth with bad grades given they are light media users is 12.87%. All right, questions? All right, if you want to go ahead and take a look at your CFU packet, take a look at just the problems right now in 5.5. Tomorrow we'll continue and do even some more practice on doing these problems in the conditional probabilities and the tree diagrams.